Welcome back, everybody. This is our sixth session in JEE Mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made 5 videos in this series, and all of those videos are available on our channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing, then you can also guide them through those videos. And if you find these videos useful, helpful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. So with this, let's start today's video. In the previous one, we completed around 25. Okay, so this was the last question. Question number 27 was the last one. And let's today start with question number 28. So total number of turns and cross-section area in a solenoid is fixed. However, the length L is varied by adjusting the separation between the windings. The inductance of the coil will be proportional to. Now we know here, as it is asked, that inductance of the coil will be proportional to. So formula for inductance of a coil, that is given by, so we can say, suppose inductance is represented by symbol H. So it will be, its formula is mu node small n square into area into length of the solenoid. Here this small n is total number of turns per unit length. Now it is mentioned that L is varied by adjusting the separation between the windings. So suppose this is our coil and we are varying its length by adjusting its windings. So means our size of or length of coil is increasing or decreasing in this way. So from this we can say that total number of turns of the coils, total number of turn, that is capital N, total number of turns of the coil is not changing, but as the length is changing, so number of turns per unit length or per unit meter is changing. So we will not use this formula here. We will substitute value small n, value of small n. So it will be mu node capital N by small n, capital N by length into AL, and it will be mu node n square A by L. So here mu node is constant, total number of turns are constant, area of the coil is constant, it is cross-sectional area, and length is variable. So we can say the inductance of the solenoid is inversely proportional to length of the solenoid. That is option D for us. Let us move to next one. So a thin strip of 10 centimeter long is in U shape wire of negligible resistance. So resistance of this wire is negligible and it is connected to a spring of spring constant 0.5 meter Newton per meter as per figure. Assembly is kept in uniform magnetic field of 0.1 Tesla. If the spring strip is pulled out its equilibrium position and released, the number of oscillation it performs before its amplitude decreases by a factor of E is N. Mass of the strip is 50 grams, its resistance is 10 ohms, and air drag is negligible, so we have to find the N. So what is happening here, that we are we can say we are stretching this strip in the, we can say, either left or the right direction, and then releasing it. After releasing it is making small oscillations. So our diagrams look like something like this, that this is our wire of negligible resistance, and here we have a strip. This is our strip. It is connected via a spring. So let this is spring. Now when we stretch it slightly, when we stretch it slightly, then due to spring there will be a restoring force, and there will be a force due to magnetic field also, that we will also discuss. But if only due to if we only consider as force due to spring, then if we stretch it slightly outwards, then it will come back again and it will start oscillating. In ideal condition it should keep on oscillating, but here we have magnetic field also, and that magnetic field act as a damping force, so that will slowly dampen out the oscillation, and finally it will comes to the equilibrium position again. So this will be the basic of the question. Now let's find out the direction of the forces and all other stuff. So we know that if we stretch it slightly outward, then restoring force towards the center or towards the mean position. So suppose this is its mean position. Suppose this is the mean position and we stretch it slightly outward. We stretch this strip up to here. Then at this point, restoring force of the spring will be towards the center, towards the mean position, as we know that spring always restoring force of a spring is always towards the mean position. And now coming to the, as this will act as a conductor, and in a case of conductor we know that force or EMF induced is given by is B into L cross V. This is the EMF induced, and force on a conductor in a magnetic field is given by I L cross B. Now if we look at the this induced EMF that is due to the motion, as our strip is moving in the positive x direction, our strip is moving here in the positive x direction, so EMF will be induced in a such way that it opposes this motion. So EMF will be induced in a such way that it opposes this motion of the strip in the positive x direction, and that can happen if the force that is induced due to this EMF, the force that is induced due to the SMF, how there will be force, we will have EMF is equal to BLV, and due to this EMF there will be current, that current will be BLV, that is induced EMF divided by the resistance. This is the current. And now from this we can find out that if we have a conductor and in that conductor there is a current flowing of this value, and that conductor is moving in the magnetic field, then force acting on that conductor is given by this formula IBL, as L and B are again at 90 degree to each other. So this will be BLV by R into LB, or it will be B square L square into V divided by R. So when we move this strip in the positive x direction, there will be an induced EMF. Due to that induced EMF, there will be a current in the circuit, and due to that current in the circuit, there will be a force acting on this strip, as this strip is carrying a current and it is moving in a magnetic field. Now this force should be such that it opposes its cause, and its cause is this velocity. So this force should also be in the opposite direction of this velocity. So here total force acting on this strip, it will be given by negative kx and negative of b square L square V by R. Why negative? Because both are opposite of the velocity. Both are restoring forces, acting as a restoring force. And if I rewrite this equation, it will be something like this: minus kx minus b into velocity. And this is equation of damped harmonic oscillator. Where oscillations damps as there is a velocity dependent force acting. Here this force is a velocity dependent force, as there is velocity in the expression here, as we increase the velocity, amount of this force is also increases. As velocity is 0, there is no damping. So from this, damping constant B will be B square L square divided by R. And we know that amplitude damping, that in case of a damping oscillations, amplitudes follows this relation, that A is equal to A node e raised to power minus bt by 2m, where m is the mass, b is the damping constant. And from this, we can use this expression to find the time period, that what is the time period, what is the time taken to reduce the amplitude by factor of e, as it is asked in a question, that number of oscillation we have to find out, after which the oscillation amplitude decreases by factor of e. So our final amplitude is a node by e is equal to a node e raised to power minus bt by 2m. A node get cancelled. We have 1 by e is equal to e raised to power minus bt by 2m. Taking logarithm of both of the sides, we will get 1. ln e is equal to 1 should be equal to bt by 2m. And from this time period, for the time it took to reduce the amplitude to 1 by e times, will be twice of the m divided by b. Now we can substitute value of b here, so it will be 2m capital B L square and r here. So time it will take twice the mass of this strip. Mass is 50 gram, resistance is 10 ohm. So 50 into 10 raised to power minus 3, resistance is 10 ohm, divided by magnetic field and the length. Magnetic field is 0.1 and length is 10 centimeter. So 0.1 is 10 raised to power minus 1, and 10 centimeter means 10 into 10 raised to power minus 2. Oh, sorry, square of this also. 10 into 10 raised to power minus 2, that will be 10 raised to power minus 1. So 10 raised to power minus 1 square. So this will be 50 into 200 into 10,000. So this whole term get cancelled. And we will have 10 raised to power minus 2, 10 raised to power minus 2. So it will be 10 raised to power 4 second. So time it will take to reduce the amplitude to 1 by e second, or 1 by e times of the original amplitude, is 10 raised to power 4 second. And why it is happening? This is happening due to damping, and that damping is produced by the induced EMF. Now we have to find number of oscillations, and for number of oscillation we need to find the time period, and time period is unaffected by the damping force. So time period stays the same. Time period will be under root m by k, where k is spring constant, m is the mass of the oscillator. So it will be 2 pi, mass we know 50 into 10 raised to power minus 3, divided by spring constant, that is 0.5, or 5 into 10 raised to power minus 1. So this will be 10 raised to power minus 2, with 10 going upwards, it will be 10 raised to power, we can say 10 raised to power minus 2, 10 raised to power minus 3. So we can write it like 1 by 1000, because we have 10 raised to power minus 3. Sorry, wait a minute, not minus 3. This will become 100. So it will be 1 by, yes, it will be 1 by 10, sorry. So this is 10 raised to power 2 into 10 raised to power minus 3, 1 by 10. Now we can do like this, bring this pi into inside of square, that will be pi square by 10. and we know pi square is almost equal to 10, so these both get cancelled, and time period will be 2 seconds. So we have the time period and we have the amount of time it took to reduce the amplitude to 1 by e times. So number of oscillation will be total time taken by the actual time period. So 10 raised to power 4 by 2, that will be 5 into 10 raised to power 3 oscillations, or 5000 oscillations. And that is option C for us. Now let's move to the next question. A 10-meter long horizontal wire extends from northeast to southwest. So let's first draw the directions. Now our wire is from northeast to southwest. So normally this is north, south, east, west. So wire is something like this. Our wire is something like this. And it is falling with the speed of 0.5 meter per second at right angle to the horizontal component of Earth's magnetic field, and horizontal component's value is given this. The value of induced EMF in the wire is, now horizontal component of Earth's magnetic field is from south direction to the north direction outside of the Earth, means on the surface of the Earth. So our horizontal component is something here. So this is our horizontal component. When we have to find induced EMF, we know induced EMF is given by B into L cross V. Now this wire is means going downward, as it's mentioned. Here it is, that falling speed is 5 into 10 raised to power minus 10 meter per second. So this wire is going downward. Now here downward means it is moving in the negative z direction. Here means it is going into the into the plane of this screen, and so our velocity is negative z direction. Magnetic field we can say in the y direction. Here if we write the directions, magnetic field is in positive y direction, so it will be, we can say J. Our velocity is in minus k direction. So for induced EMF, our length needs to be in the, we can say, x direction, or we will take as it is already mentioned that it is at northeast and southwest, means it will be making equal angle with both of these sides. So this angle will be 45 degree, and length is 10 meter. So x component of this wire, that will be L cos 45. We have to take this positive side and negative side, both of the sides also. So wire needs, first of all, wire needs to be in the x direction or I direction. Sign does not matter, positive I or negative I, but it needs to be the length which needs to be taken, it will be of along the x direction, and that length will be L cos 45. So now write the formula. We have magnetic field as 3 into 10 raised to power minus 5 into length will be 10 by root 2, and we have magnetic velocity, that is 5. So this will be 50 into 3, 150. Sorry, note 5 into 3, 15 by root 2 into 10 raised to power minus 4. And solving this, we can write it like 10.64 into 10 raised to power minus 4, and that will be 1.06 into 10 to the power minus 3. So the answer which closely resembles that is option B. Now, if in this question, this angle, suppose if this angle is 60 degree, then our x component of the wire becomes L cos 60. And depending upon the angle, the component changes and the value of EMF will also change. And if this wire is along the north-south direction or the south-north direction, there will be no induced EMF. Why? Because length of the wire and the magnetic field both are in the same direction. Here, to get a value out of this formula, here we have a dot product and here we have a cross product. So these two cross products must be in the same direction or in the opposite direction of the magnetic field. And that can only happen when all of these three are in the different direction. If this is in X, this is in Y, then this should be in the Z direction. So magnetic field, length and velocity, all of these three in the different direction, only then we can get an answer from this formula. Now, let's move to the next one. There are two long coaxial solenoid of same length L. The inner and outer coils have radius R1 and R2 and the number of turns per unit length N1 and 2. The ratio of mutual inductance to the self-inductance of the inner coil. So first we have to find the mutual inductance and then the self-inductance. So mutual inductance that represented by M and self-inductance by L. So mutual inductance will be given by mu node N1, as mutual inductance is for both of the coils. So it will be mu node times N1, number of turn unit per unit length for first solenoid, N2 for second solenoid, into area multiply by the length. Now this area is the area of the solenoid for which we are taking we are calculating the mutual we can say mutual inductance, and as we are doing it for the inner coil, so area will be pi r1 square. So it will be mu node n1 n2 pi r1 square into length. Now self inductance for the inner coil will be mu node n1 square, same length, yes, inner have for first we have symbol n1, so n1 square into pi r1 square, its area into its length. So this is mutual inductance and this is self inductance, and if we divide both of these, m by l, it will be n2 by n1, that is option D for us. Let's move to the next one. A copper wire is wound on a wooden frame whose shape is that of an equilateral triangle. If the linear dimensions of each side of the frame increase by a factor 3, keeping the number of turns of the coil per unit length of the frame is same, then the self-inductance of the coil will be. So we have to find out self-inductance, and it is mentioned that it is in the shape of an equilateral triangle. So the formula for self-inductance is given by mu node n square into area into length of the coil. So here it is mentioned we increase the length in such way that number of turns per unit length is constant. So small n is constant, but length will change and area will change here. So suppose this is the initial equilateral triangle that we have, each of side A. Now area of this triangle will be given by, if we draw a perpendicular here, So it will be, area will be twice of the half, base will be a by 2 into perpendicular. This perpendicular will be a square minus a square by 4, that will be root 3a by 2. That we can calculate like this. It will be a square minus a square by 4. This is a by 2. So a square by 4, from this we get this. So area is equal to root 3a square by 4. This is initial area. Now we increase each side by a factor of 3. So means each sides become 3a. So our each of side becomes 3a. This is 3a, this is 3a, this is 3a. Now new area a dash will be twice again half of the base, that is 3a by 2. This base is 3a by 2 into perpendicular. That perpendicular will be 9a square minus 9a square by 4. So that will be 36 minus 9, 27. A square by 4 under root, and that can be written as 3 root 3 a by 2. So 3 root 3 a by 2 to get cancelled again, and this is 9 root 3 a square by 4. Now coming to the length, as we have length also in this formula. So length of this solenoid will be 3a, and for this solenoid will be 9a. So now we can divide L dash by L, that will be mu node n square. Area of the new triangle will be 9 root 3 by 4 of a square into its length will be 369a divided by the original triangle, or we can say original mutual inductance, self inductance, mu node n square. N is same as per mentioned, that turns per unit length of the frame is same. So old area will be root 3a square by 4 into old length was 3a. So this goes on 3, 4 cancelled, root a square get cancelled, root 3 is cancelled, n square and all gets cancelled. So we have 9 and 3 left, so it will be 27. So mutual self inductance of the coil increases by 27 times. That is option B for us. Let's move to the next one. So a solid style metal cube of edge length 2 cm is moving in a positive y direction with constant speed of 6 meter per second. There is uniform magnetic field in the positive z direction. The potential difference between the two faces of the cube perpendicular to the x-axis. So first of all, let's draw the axis. Suppose these are our axes, and we have a cube. Suppose this is our cube, and the cube is moving in the y direction. So it is moving upward. Y, X, Z, and our field is in positive Z direction. This is magnetic field. Now we have been asked that potential difference between the two faces of the cube perpendicular to the x-axis. Now the faces which are perpendicular to the x-axis are this face is perpendicular to x-axis, and also this face is perpendicular to x-axis. If we look according to the plane of the face, these two planes will be the perpendicular to the x-axis. And if we look as per the area vector, then this face and this face, these two faces will be perpendicular to the x-axis. Now, so there is slight confusion that about which axis we have to discuss, and also these two faces, the front face and the backward face also will be perpendicular to x-axis as per the, we can say, if we look towards the plane of the x-axis, plane of the faces. So to not to get confused, what we do, we directly use the formula for the induced EMF. Now, for induced EMF, we know that it is given by B L cross B. This is the induced EMF formula. And here, our magnetic field is in Z direction, so it is in K. Let's leave the length now. And our velocity is in the Y direction, so it is in J. So length should be in the X direction. Only then we get a EMF or potential difference. Now coming to this, if I rub this, and if I draw this sphere in a cube in a slightly bigger so that I can make it understand. Suppose this is our cube and it is moving with upward velocity. So now length of this face is parallel to the velocity. Length of this face is parallel to velocity. So in this face there will be no induced EMF. Similarly for this face, again length is parallel to the velocity. For this face also we can say length is parallel to the velocity, and for the upward face also length is parallel to the velocity. Now actually length is decided as per the, we can say, direction of the current, but here we don't have the direction of the current. But in every case length will stay the same, that is 2 centimeters. So it does not matter that which length we are taking, it will stay 2 centimeter. So simply we can write induced EMF will be B into L cross V. Value of magnetic field is 1 Tesla, 0.1 Tesla. Length is 2 centimeters, so 2 into 10 raised power minus 2, and velocity is 6. So this will be 12 into 10 raised power minus 3, or 12 millivolts. That is option A for us. Now with this we end this video here, and if you found this video helpful, useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.